Welcome everyone. Today we're going to talk about compressibility drag. So we've discussed parasitic drag, which is the drag due to really viscosity, induced drag, which is driven by lift, and today compressibility drag, which is driven by high Mach numbers, the compressible nature of a fluid. Okay, so here's just a summary of that, right? These are the three components of drag that we're going to talk about today is compressibility drag. So first we need to talk about shock waves. Let's do a bit of a thought experiment here. Let's imagine, we've all seen this, if you go to the river and there's a rock in the river, fluid, the water diverts around the rock well before it gets to the rock, right? You can see upstream, if you threw a new rock in, it's going to change the flow around and it's going to divert ahead of the upstream of the rock. Well, how does the water know to do that? Of course, the pressure of the rock in the fluid is transmitted through the fluid, and pressure is transmitted at the speed of sound, in this case, the speed of sound in the water. So if we took that same example, we took the rock and now we throw it through the air, same thing happens, right? As the rock is flying through the air that's here is a still molecule. As the rock approaches, feels that pressure, right? And starts to move around the rock, right? It's going to move around as that rock comes by, because as the rock comes by, those pressure waves are moving at the speed of sound in all directions. Okay, well, what happens if I throw that rock faster and I start to approach the speed of sound, or I exceed the speed of sound? What's going to happen then in that case? Okay, to get you thinking about this, let's just draw a rock here. Here's our rock, and it's going at Mach 0, so it's not moving. There's a fluid, so the pressure waves around it would just be circular, right? Pressure would just radiate in all directions, and to maybe not think of it as a rock and pressure waves, which may seem hard to think about that. It doesn't quite make sense. Let's say it's a sound source, like I got this little speaker that just beeps, pulses a sound, okay? So it's not moving, it's sending sound waves in all directions, speed of sound. Okay, well, I want you to think about a few scenarios here. Now I've got my rock, and let's say it's going to the right. I'm going to throw my rock to the right, okay? Here's this case, the Mach number is less than 1, the Mach number is equal to the 1, and the Mach number is greater than 1. So in all three cases, I have a rock. I threw it at these different speeds, and I would like you to now draw what those contours are going to look like, right? These are these acoustic contours of sound radiating off of this little pulsing speaker that we threw. So just take a minute, try and draw those. Okay, so imagine the Mach number less than 1 case. If the Mach number is less than 1, the rock or the speaker is still radiating sound in spheres, but because it's traveling to the right, it's going to kind of catch up. Say it emitted a sound pulse here. It's going to move in that same time that noise contour moved, and so it's going to kind of bunch up like this. Right? They're going to be more bunched up on one side versus the other, and you're familiar with this as a Doppler effect. But let's keep going with it. What happens at Mach 1? If the Mach number is exactly 1, then any noise that I emit at any instant, it sends some sound wave, but I'm traveling at exactly the same speed as that sound wave. So let's say I emitted some noise at this instant here, and it generated a circle around to that point. I'm going to be right at the edge of that sound wave. So all of my sound waves are going to start bunching up right here at the point where I'm at, because all of these were emitted at some later past point in time, but I'm now right on that front. Now what if I exceed Mach 1? Okay, well, I emitted some sound wave at this time, but I've now flown even faster than that sound wave is even traveling. So what is that going to look like? Well, here's one that I emitted recently. One that I emitted a while ago has grown bigger, but it's farther away. One that I emitted even further back is back here. And I'm going to get this cone shape. We call this a mock cone. There's a little visual that I think does this pretty well. Let's flip over to a website here. I think this is Penn State. Doppler. Let's see if I can find this real quick. Yeah, so here's a good visualization. Here's that first case, right? Stationary sound source emits it as spherical waves. Now I'm moving at less than the speed of sound. You can see that the sound source moving to the right, get it bunching up towards the front. If I move right at Mach 1, I'm right on the edge of the fronts of those sound waves. And if I'm going faster than the speed of sound, you can see I'm moving outside of every sphere of noise that I emit. I'm even going faster than that, and you can see that kind of cone shape that's forming. Okay, so let's think back again to our analogy with the rock. What is happening? So if I'm through this rock and it's putting pressure on the fluid that's being transmitted, here I am, an air particle. I see that rock coming. I know it's coming. I can feel the pressure waves. I can start reacting and I can start moving. Well, what if I am now, in this case, where the Mach number is greater than 1, I'm an air particle here, or I'm even an air particle here. Notice that I am outside of that Mach cone, meaning when I'm here, I do not know that rock is coming until it's already there. Even in this case here, I don't know the rock is coming. I cannot feel that pressure wave, even until it's passed, until this Mach cone hits me. Okay, and so this is a problem in some sense, and this is why we have shock waves. In the subsonic case, the fluid can gradually move around some object. Here, I'm an air particle minding my own business. I don't know anything is happening, and then suddenly, when this Mach cone catches up to me, things have to change essentially instantaneously. I now know that there's this big pressure wave coming, but it's already here. There's no time for me to divert around. So what happens is that the fluid properties change effectively instantly through what's called a shock wave. Now a shock wave and a Mach wave are not exactly the same. We may talk about that a little bit more in a little bit, but conceptually it's going to be a very similar idea. A Mach wave is actually, it's an infinitely weak shock wave because these are just sound pressure levels, but for a stronger disturbance, we get a shock wave. It's going to have a steeper angle than this, actually. And through that shock wave, it's really like a boundary layer. It's not necessary. It's not really instantaneous, but from an engineering or from a macro perspective, it is because it's so thin, very, very thin, viscous layer where the pressure, the density, temperature, all the fluid properties change, and the direction of the fluid has to change effectively instantly. Okay, and then this is accompanied by these big changes in pressure waves is something that we're going to hear because there's this jump in pressure. In fact, across an airplane, there's going to be a bunch of pressures and they'll kind of bunch up typically in something like an N wave where we'll hear a big pressure jump and a pressure drop, which is kind of the sonic boom that you may have heard of. Okay, so we're going to talk about three regions of compressible drag. The behavior is not quite the same in all three regions. Okay, so the first, let's see. I'm just going to add a slide real quick. See if I can do that. Okay, not sure that worked, but let's just do this right here. Before, when we talked about parasitic drag, okay, we saw that drag was equal to this is the parasitic drag coefficient times the dynamic pressure and some reference area. Induced drag is going to follow same formula, of course, except for now the induced drag coefficient varies with lift, CL squared over pi aspect ratio. Actually, let me just write this differently. In fact, this is true generally. So there's some parasitic drag coefficient we can calculate. And just by definition, this is really the definition of drag. It's a drag coefficient times the dynamic pressure times the reference area, right? That's just by definition. And the drag coefficient is going to be the sum of the parasitic drag coefficient, induced drag coefficient, and then compressibility drag coefficient. So the question is, what does that compressibility drag coefficient look like? The parasitic drag coefficient really is just a function of Reynolds number across a decent range. It's not going to change too much usually. Induced drag coefficient is a function of the lift coefficient. So if we're at constant lift, relatively constant Reynolds number, those are going to be constant. What about compressibility drag coefficient? Since these are all non-dimensional numbers, right? They depend on non-dimensional numbers. Parasitic drag is a function of Reynolds number. Induced drag coefficient, a function of the lift coefficient. What about compressibility drag? What should it be a function of? Okay, the natural one here, of course, is Mach number, right? The ratio of my speed to the speed of sound. What does that curve look like? Take a moment and see if you can predict what that might look like as we increase Mach number. Okay, so here's a typical behavior. This first part, I think many of us are aware of, this kind of drag rise. So it's actually constant for quite a while. As you might expect at low Mach numbers, it's essentially incompressible, so there's really no impact of compressibility drag. There may be some slight rise, but at some point, it starts to increase precipitously. And Mach 1 may not be quite at the peak, but generally somewhere around there. It's going to rise steeply, and this was known as a sound barrier for some time. Although it was common or maybe popular to think that before we crossed the sound barrier that people thought it was an actual barrier, but we knew, of course, long before we flew past the speed of sound that this was not an actual barrier. Projectiles had been shot faster than Mach 1 for quite some time before that, but for aircraft, it's still called a barrier in the sense that this is a lot of drag you have to overcome, right? And but it does, at least the drag coefficient, not necessarily the drag, but the drag coefficient does start to decrease again, right? And it generally peaks around Mach 1. Just in terms of nomenclature, we call this point here, which has various definitions, but roughly speaking, we call this the drag divergence Mach number. And by definition wise, we would say it's, again, roughly speaking, it's about the point where the drag starts to increase rapidly. Okay, and there are some, like I said, some mathematical definitions about what the slope needs to be. But for a point, it's kind of the point where if you're a transport aircraft, generally going to fly pretty close to that point, right? We don't want to exceed that. We're going to be paying a big price in fuel, but we want to get there as quick as we can. So we're going to be pretty close to that area. Crest critical, CC, it's just another name that's used, which kind of refers to at the crest of the airfoil, it's the top of the airfoil, it's when supersonic flow first occurs there. So not too important for this present discussion, but just going to point that out. An important concept, though, to realize is that to have transonic, this drag rise or this compressibility drag, I don't need to be flying at supersonic speeds or near Mach 1, right? I can be flying at speeds well below Mach 1. And here's a picture that helps demonstrate this. These are actually pressure contours, but you could think of them as Mach contours. They're going to look very similar. So here, this airfoil is going at Mach 0.6, and let's say the green corresponds to 0.6. And again, these are really pressure, but there's going to be a really close correspondence to Mach number. There's going to be a low pressure, a high speed up here. And so even though the free stream is at Mach 0.6, the air moving over the airfoil at some points is going to exceed that. And at some point, as I increase in speed, this air passing over the airfoil or the wing may exceed Mach 1. If it does, I'm going to have a region of supersonic flow, and the only way for that to terminate, except for in some real, somewhat contrived cases, it has to terminate with a shock wave. Okay, so I'm going to speed up to supersonic flow. For that supersonic flow to return back to subsonic, which it needs to, right, to return to this boundary condition of I'm going to have free stream, far upstream and downstream, there's going to be a shock wave. This is going to be, like I said, kind of like a boundary layer. It's a high entropy process, irreversible process, lots of drag associated with that potentially. Okay, so it passes with a shock wave. If I'm going even faster, And these numbers are kind of typical, you know, a transport aircraft that you fly in is going to be somewhere around Mach 0.8. That as you speed up over the airfoil, you're going to have regions of supersonic flow and potentially terminate in a strong shock wave. Now, we want to design the wing and the aircraft so that these shock waves are weak. There's a region where a relatively weak shock wave doesn't have large entropy increases. It's relatively flat, and then it starts to increase quite dramatically in terms of entropy increase and drag increase. So we try to keep these relatively weak. But the main point here that we need to keep in mind is that I do not need to be flying at supersonic speeds to have this compressibility drag. Even flying at these subsonic speeds, because the air is going to speed up over parts of the aircraft, I'm going to have regions of supersonic flow that terminate with shock waves, reducing it back to subsonic, and those shock waves can create a lot of drag. Okay, so one idea that's really, well, a really impactful idea in flight, especially for transport aircraft, is what's called simple sweep theory. Simple sweep theory was developed independently by Adolf Busemann in Germany and R.T. Jones in the US around the time of World War II, I think just about after that. So R.T. Jones, he had proposed this idea using some concepts from subsonic theory. And one way you could think of it, well, I'll just say real quick, you know, there's an interesting history you can look at, but he had proposed this idea about simple sweep theory and how it could allow us to fly at faster speeds without incurring this big drag rise. The idea was, well, sorry, let me just explain this. He proposed this idea again. There was some, from subsonic theory, some mathematical and some intuition that kind of led to it. And he had a paper on it, and some folks inside the NACA at the time did not support it, did not agree. They delayed publication, and they did some experiments finally where they dropped these swept projectiles and showed that indeed you could fly much faster or drop them much faster, these higher Mach numbers, without incurring this drag rise. So it was ultimately vindicated, and again, right about the same time, they realized that this had also been developed in Germany. So here's the basic idea, and then we'll try to get some intuition behind it. The idea is that if I sweep my wing, right, so here you can see a swept wing, sweeping it back, actually this works forward too. If I sweep the wing, the only Mach number that really matters is this normal component, the component that is normal to the sweep angle. So if I'm at 90 degrees, just a straight wing, my full free stream speed, that Mach number, that's the important one. But as I sweep, then the Mach number that matters is the one that's perpendicular to the sweep angle, okay? That's a big deal because this is gonna be equal to my free stream number times the cosine of the sweep angle, where say this is my sweep angle, right? So this is my sweep angle. So by sweeping the wing, what I'm doing is that I'm effectively reducing the Mach number that the wing is experiencing. In other words, I could fly faster, right? If we think back to that last picture, say that I'm starting to get significant drag rise at like say Mach 0.65 or something, that by putting a little sweep, my free stream speed might be Mach 0.8, or in other words, the speed I'm flying at might be Mach 0.8, but my wing is experiencing effectively a Mach number of 0.65, and so the drag has not increased. I've delayed the amount of drag that I'm experiencing while still being able to fly faster. So this is a big idea, right, that of course has changed air transport, that we can fly at these much faster speeds by sweeping the wing. Let's try to motivate it a little bit, why this might be the case. Here's one way to think of it. Imagine I had a wing that was infinitely long, okay? Infinitely long, this wind tunnel, and it has some velocity coming in. This is gonna be the Mach number. I'm gonna call it the normal component for now, okay? And now, this is just gonna be a thought experiment. We're gonna remove viscosity from the world because this is not, this effect is really, is influenced somewhat by viscosity, just like lift is, but effectively it's an independent thing of viscosity, right? This will occur even in inviscid. In an inviscid scenario, we would still have these shock waves. So imagine I've got an inviscid wing, and it's an infinite wing. I'm now going to start sliding it, right? So it's like a conveyor belt wing, I guess. It's this infinite wing. I'm just moving it along. Because it's inviscid, the fluid around it isn't going to be dragged with it, so it doesn't really know that that's the case. Okay, that doesn't really matter. But because it's moving, then the relative inflow into the wing is going to look like this, right? There's going to be some tangential component. So this is my actual free stream component. Or another way to think about it, if you don't like the moving wing thing, let's say I just, instead of having the air come normal, I put it at this angle. So there's a normal component and tangential component. Because there's no viscosity and it's an infinite wing, that tangential component contributes nothing. It doesn't change anything about the behavior of each airflow section. There's no way it can because it's infinite, right? And there's no viscosity for, like, say, a boundary layer developing spanwise. So the only thing that's going to matter from this perspective, again, in this sort of idealized world, is this normal component. You could think about this, this drawing here. Well, this is exactly the same if I had a infinitely swept wing. If I just rotated the wing this way, here's my normal component, tangential component. This is exactly the same scenario. The free stream is this way. So in other words, if I take my wing and I sweep it, I would think, again, in this idealized case, the normal Mach number is the only thing that's going to matter for predicting how this drag should be, or how compressive wave drag should be affected. And indeed, of course, like, this is not a perfect analogy, but it's works really, really well, surprisingly well, this simple idea. There are some formulas in the text and more sophisticated ones you can find in various published papers, but you'll see predominantly, right, this cosine of the Mach number appear in these, right? Because again, this normal Mach number plays a critical role in the physics of the problem. Okay, so again, the key idea here is that if I fly, let's say I was flying a straight wing and Mach 0.6 was causing too much drag, well, I could sweep the wing. Let's just calculate this real quick. Let's say I swept it 30 degrees. I guess I'll have to divide. I'm just trying to calculate this real quick. So let's take 0.6 divided by cosine of 30. That's about Mach 0.7. So for the same effective Mach number, if I swept, like, say, 30 degrees, I could get up to Mach 0.7 with no increase in drag, more or less. So that's, again, been a big revolution in air transport. Okay, so that's what we'd call transonic wave drag. And again, well, not again, I didn't say this. The reason why we call it transonic, that just means near sonic. Although the cases we've been talking about are really sort of subsonic, but that's often what we refer to as the transonic region, somewhere in, like, say, Mach 0.6 up to Mach 1. Sometimes transonic, we say above it, but supersonic, by definition, means above, above the speed of sound. And when you're above the speed of sound, things are quite different. We don't have, well, obviously the free stream is now supersonic, so we don't have these pockets of subsonic air that then speed up to supersonic. It's supersonic to begin with, and so we're going to have shock waves throughout the flow field. In this class, we're not going to dive too much into, well, we're not going to dive into the math of compressible flow, but I'm just going to give you some intuition here. The ideal case, if you're at subsonic flow, is to have what's called an oblique shock wave. An oblique means it's at an angle. So if you look at these lines here, this is a Schlieren image. These are like density contours. And the density jumps dramatically across these shock waves, so we can visualize them. You can see these lines, which are shock waves coming off of this wing mounted to the sting in this air tunnel or wind tunnel. Notice how they come off at an angle relative to the wing. We'd call this an oblique shock. If it was straight, we would say that's a normal shock wave. So we want these oblique shock waves. Remember how we talked about the Mach waves? The Mach waves are like an infinitely weak oblique shock wave. We just keep tilting it further and further, and there's a point, the angle for the Mach wave is just, it's a function of the Mach number. that would be infinitely weak. As these become steeper and steeper, they become stronger and stronger until we get to a normal shock wave, which is the strongest, and that's associated with big drag losses. So we want these oblique shock waves. The way we do that is that we need to have sharp points. So we have, you'll notice this with supersonic aircraft, right? Like sharp noses, sharp edges on a lot of the wings. And we also need long dimensions. So the aircraft is going to be long relative to its diameter. So you'll often see these big, long noses in the front of these supersonic aircraft. In fact, many of them now will add even these spikes, even on the front, to make it even longer, just to try to increase the effective fineness ratio of the aircraft to make these oblique shock waves. Another consideration in designing these aircraft in supersonic flight is what's called the area rule. The area rule, you could think of it this way. Imagine I took my aircraft and I just chopped it up into these different cross sections. So here's one cross section, right? And here's a cross section where the fuselage has a circular cross section, but there's some part of the wing. And if I was to plot those on a curve, right, I would want, I believe it's the second derivative of the area actually that we want to be quite smooth. So I need the smooth, roughly speaking, the smooth distribution area. If it's kind of bumpy and I've got like a big jump from the wing, another jump from the tail, then that's going to cause a lot more drag. So I need this kind of smooth shape and drag. So often, some of the older aircraft, you'll see this, they'll have this Koch bottling effect, where because there's an increase in area of the wing, they're going to decrease some of the area in the fuselage to compensate, so you get this smoother area distribution. It's actually more complicated than that. We need to take cuts not just in this normal direction, but along, let's say, these Mach contours, the Mach lines, or the Mach angles rather, of all the various Mach numbers that we're going to fly at. So, you know, if we may fly across a range of Mach numbers, we got to make sure the area distribution is smooth across many different ways to cut up this aircraft. So that can be a complex procedure. All right, so even if we have a sharp nose, at some point, if we increase the Mach number enough, it doesn't matter how sharp it is, the shock wave is going to detach. Or if we have a blunt body, it's not sharp to begin with, we're also going to get what's called a bow shock, as you can see here. So here's a projectile. It's got a blunt shape, not a sharp shape as before. And the shock wave in front is what we call a bow shock. It's detached from the body, whereas before those oblique shocks, you could see it came right from the nose, from the wing, those are attached. This one has this distance, it's offset from the body. So it's a detached bow shock. And here you can see this front part is perpendicular to the flow. So this is a normal shock. Again, that's the worst case, tons and tons of drag associated with that. And we actually pass through a whole range of oblique shocks here, all the way out to a Mach wave. But in general, this shape is going to give us a lot of drag. And again, that's going to occur anytime we have a blunt shape. But even with a sharp shape, at some point, it's going to occur eventually as we increase the Mach number. Now, generally for aircraft, that's undesirable, but there are also many aerospace cases where we want this high drag, right? Of course, so on a reentry vehicle is a classic example. Reentry vehicles coming back down to Earth, and of course, they have these blunt shapes because we want a lot of drag. We're trying to slow it down through the atmosphere. There are also reasons for aerodynamic heating, actually, that we want this offset so it can be desirable, but in general, it really helps us to increase drag. Okay, there are a few more details if you're interested in the book about some equations that can be used. Those obviously don't apply to our aircraft that we're designing in this class, so we're not going to spend too much time on them, but for those of you who are interested, I encourage you to go check that out. Okay, so next time we're going to start talking about, I believe, airfoils and wings in a little more detail. This is going to kind of wrap up our overview of drag. Let me just check the schedule real quick. So airfoil and wing design, that's going to be coming up next week. All right, take care, everyone.